welcome back to CMOS RF integrated circuits. Today is lecture 17, part of the 6th module. We have been talking about wideband amplifier design, and today we are going to look at trade-offs between bandwidth, group delay and peaking. Now, we are going to continue from where we had left off in the previous class, in the previous lecture. So, in the previous lecture, what we were really discussing is this particular network. So, instead of trying to drive a load which is just R and C parallel combination, why don't I try to drive something that looks like what has been projected. So, L in series with R, in shunt with the load capacitance. So, this is what we are trying to drive, and we came up with the transfer function. This was the transfer function. The ZL earlier was the transfer function before, and ZL now is the transfer function now, and then we were really busy trying to trying to find out what is the bandwidth. So, we came up with the rule for bandwidth. The rule for bandwidth is omega at which magnitude squared is equal to half, and magnitude squared is equal to half of the magnitude squared at DC, right. So, just remember that, and then we tried to solve for omega. Instead, we ended up solving for omega squared, and we found that omega squared has two roots given by the above two. Now, what do you think? Let me simplify a little bit more on this. So, I am going to multiply the numerator by eta squared, denominator by eta squared, and that will give me 2 plus 2 eta minus eta squared minus plus square root of 2 plus 2 eta minus eta squared whole squared plus 4 eta squared divided by 2 tau c squared. Okay. So, this was the expression for omega squared. Now, omega squared is a positive quantity, it has got to be a positive quantity. The two roots are both real numbers, thankfully, but otherwise if this quantity is so much, this quantity is going to be more than that. It is the same x squared plus something under root the whole thing. So, it has got to be, so the second term is more than the first term, which means that the minus result, this one, will give you a negative value, net will be negative. Now, omega squared, omega is a real number, so omega squared has got to be positive. So, we are basically going to ignore the negative root for omega squared, and as a result omega squared is basically going to be 1 by 2 tau c squared times this is my net result for omega squared, which means that omega is a further square root of this. Fine. Now, suppose I want to maximize this. I want to maximize my bandwidth. This is the bandwidth. Okay. Original bandwidth was 1 by tau c, remember. So, the new bandwidth is something like a factor more than 1 by tau c squared. Bandwidth squared is a factor more than 1 by tau c squared. So, simplify a little bit more. Okay. So, first of all, when is the bandwidth going to be more than the original? Whenever this factor is more than 1, I am going to get it to be more than the original. And when is it going to be greater than 1? When is it, at what eta is this equal to 1? We can solve for that eta. Okay? That is the eta beyond which you are not going to get bandwidth enhancement. You are only going to reduce your bandwidth. You are going to pay a penalty in terms of your bandwidth. So, we do not want that to happen. Fine. Next, what is the maximum bandwidth that is possible from this? How do you find out maximum? You do a derivative, you put the derivative equal to 0, that will give you some kind of maxima or minima. Hopefully, the second derivative is also in the right direction. You will get a maximum, really. I mean, as you change eta, you are going to get some eta at which the bandwidth is going to be maximum. Okay. So, can we find out the bandwidth at which the eta at which the bandwidth is maximum? So, let us do the derivative of this quantity, derivative with respect to eta. So, let me call this f of eta. Derivative of something under a square root, derivative of x power half is half of half times x power minus half, right. Okay. So, this is the derivative, and let me simplify this a little bit because it is quite unwieldy. Okay. So, this is what I have got, and for a maximum to happen, this quantity has got to be equal to 0. Now, instead of going through the entire algebra, let me just try to plug in one number. So, let us try to plug in eta equal to square root of 2. I mean, you can do it, you can solve this, but let me just first try to plug this in to make life easier. So, if I do plug that in, I get 1 minus root 2 plus 2 plus 2 root 2 minus 6 plus 2 root 2 divided by 2 times square root of 1 plus root 2 minus 1 the whole squared plus 2. So, this simplifies 1 plus square root of 2 minus 1 is basically square root of 2, whole squared is 2, 2 plus 2 is 4, square root of 4 is 2, 2 times 2 is 4, and 2 root 2 plus 2 root 2 is 4 times root 2, and 2 minus 6 is minus 4. And you divide numerator and denominator by 4, and lo and behold you end up with 0. So, instead of solving the complicated equation, thankfully I already knew the root and I plugged it in, and I satisfied to you that that is indeed a root. So, when I do plug in eta equal to root 2, I should be getting the maximum bandwidth. You can do the second derivative of this and satisfy for yourself that the second derivative is indeed the right sign. Second derivative has to be negative. Okay. So, that you can satisfy for yourself, and so basically what I am trying to say over here is when you do plug in eta equal to root 2, you get the maximum possible bandwidth. So, what does your transfer function look like when you plug in eta equal to root 2? Or rather, where do the poles and zeros show up when eta is equal to root 2? You get the two poles to be at these two complex locations, right. Remember, we did this in the previous class, kind of did this. right, and we have got a 0 at what frequency? Zero in the left half plane. Okay. So, these are the locations of the poles which are not the same as okay, it's fine. So, let me simplify this further. I am going to divide numerator and denominator by tau c. And then what I am going to further do, which is fine. Okay. So, this is what we have really got. Somehow this is not the same as the previous result. Why is that? I would believe that there was a mistake in the previous result. This should not have been 2 times root 2, this should have been 2 times tau c, which tau c also I inadvertently substituted by root 2 and you did not catch it. Okay. So, anyway, so these are the locations of the 2 poles. Now, 2 is definitely less than 4 times root 2, which means that the quantity under the square root is negative, which means that the locations of the 2 poles are imaginary. So, let me take out j over here, and instead of doing 2 minus 4 root 2, I am going to do 4 root 2 minus 2 and divide the whole thing by 2. Okay, you could also think of it in this fashion. All right, so these are the locations of the two poles. It so happens that when you actually plot the magnitude response of this function, okay, the earlier function, if I plot the magnitude response of the earlier function, it was something like this. Right? This was the magnitude response of the earlier function. Of course, you have a log scale here and a log scale here. Okay, we like doing things in the log scale. Now, what has happened is you've got a 0. Where is your 0? You have a 0 at a frequency which is a little more than 1 by tau c, root 2 times more than 1 by tau c. So, you have got a 0 frequency right over here. Okay. Where are the two poles? The two poles will show their effect at a frequency which is root 2 times less than 1 by tau c. So, the two poles are going to show their effect somewhere over here. Okay. In the Bode plot, the real part is what matters, right. So, this is the story. So, what is going to happen is that what else happens when there are a pair of complex conjugate poles? When there are a pair of complex conjugate poles, what happens is there is going to be peaking. So, somehow this is going to be the effective transfer function. So, because of the two poles, I am going to get minus 40 dB per decade, fine. Because the poles are a complex conjugate pair, I am going to get substantial amount of peaking, and then in addition to that, a little bit after, because of the 0, I am going to get plus 20 dB per decade, as a result of which my net slope is going to be minus 20 dB per decade. So, this is the complete story. This is how the transfer function is going to look like. Now, do you want this kind of a transfer function? Do you want this kind of a transfer function? The answer is maybe, but not really. I want flat pass band. So, my 3 dB frequency has increased substantially. I agree, this is probably my new 3 dB frequency, which has dramatically improved. Okay, but I like a flat passband. How much was the 3 dB frequency improvement? We didn't really compute that, did we? Let's quickly so 1 plus square root of 2 minus 1 is really square root of 2. Square root of 2 squared plus square root of 2 squared is 2 plus 2, which is 4. Root of 4 is 2. Plus square root of 2 is something like 3.4. So, your bandwidth actually increased by about 3.4 times, bandwidth squared increased by 3.4 times. So, bandwidth increased by square root of 3.4, square root of 3.4 is about 1.8, yeah, about 1.8. So, your bandwidth improved by about 1.8. times. So, I got a bandwidth enhancement by 1.8 times, 1 by tau c. However, I ended up with substantial amount of peaking. So, this phenomenon is called peaking. Why did this happen? This happened because I was over aggressive, because of the pair of complex conjugate poles being rather close to the j omega axis. So, that is why this happened. Okay. And the way this can be avoided is by pulling the poles away from the j omega axis. In other words, you reduce your aggressiveness. Okay. So, in other words, let me increase the value of eta and I will get something better. So, one can show that if I reduce, if I increase the value of eta to let us say 1.8 or so, I am sorry 1.6 or so, then I get about only 3 dB of peaking. Okay. If I increase the value of eta even further, remember what is the maximum eta that you would like to, you can figure out the value of eta for which you will get any bandwidth enhancement by comparing this quantity f of n to 1. It should be more than 1 for any kind of bandwidth enhancement. Fine. I think that number is about 4. All right. So, eta equal to 1.8 gives maximally flat. What is maximally flat? Maximally flat is like Butterworth. Butterworth response is maximally flat. So, when the denominator polynomial magnitude squared is of the form 1 plus omega by omega naught whole power 4 in case of second order. This is the magnitude squared of the denominator polynomial. That will give me maximally flat. Our current magnitude squared is looks like something looks like this magnitude squared. Okay, fine. And then eta equal to 1.9 gives you constant group delay, linear phase. So, all of these different conditions are nice things. You want as high a bandwidth as possible. So, you would like eta to be as close to 1.4 as possible. Then you say that when I design eta to be 1.4, I get good bandwidth. Yes, I get really good bandwidth, but I get horrible peaking. So, you say that let me reduce my peaking. So, you sacrifice your bandwidth a little bit and you get only 3 dB of peaking. You increase the value of eta to 1.6. Now, you get a different bandwidth enhancement. Your earlier bandwidth enhancement was 1.8 times. Now, it is going to be something lesser than that. That is what you anticipate. You always pay in terms of something. Then you say that no, I did not really want 3 dB, I wanted a maximally flat response. So, again you pay a little more. Then you say that no, I did not even want maximally flat response, I wanted linear phase. Why would you want linear phase? Linear phase means constant group delay, means whatever the frequency is, that frequency goes through the circuit with a certain constant delay, right. It is a very desirable property of a circuit within the bandwidth. So, within the bandwidth constant group delay, you increase your eta even further, which means you reduce your bandwidth enhancement a little bit more, okay, and so on and so forth. So, of course, the lesser the value of eta is, the better the bandwidth performance. I mean 1.4 is the absolute maximum bandwidth you can get, and then you keep trading off, right. So, this is a nice circuit. It has been used for years and years together. What was the circuit like? All we are doing right now is we are playing with the load. Okay. Let me draw this in a little different fashion. Let me draw this in a little different fashion, and all right. Now, can I do even better than this? Turns out that you can do even better than this if you put an inductor over here and basically resonate out the capacitor. You can do even better than that when you put an inductor over there. Now, why would this perform even better? Let us quickly go back to our original. our original was this, right. This was the very first circuit. So, when you apply a pulse at the input, suppose you apply a step at the input, initially current was flowing through the device, now the current has to, I am sorry, initially no current was flowing through the device, now current will have to be established. So, the current also will follow a step, should follow a step. So, the current through the device is also going to follow a step, but the voltage at the output you want that to follow a negative step. So, initially the voltage was at power supply, now you would want the voltage to go down. This is the basic idea. This should be the ideal step response. Now, because there is a capacitor over there, this is not really going to happen, and even when the current goes through a step response, because the load is an RC, the capacitor is going to charge up slowly. Okay. So, this is what you are going to achieve out of this first cut. Now, what I do is I say that forget the first cut, let us now talk about the second cut where I have put an inductor over there. Now, what is the property of an inductor? An inductor likes to keep the current through it a constant. This is the most, this is a capacitor likes the voltage across it to be a constant, an inductor likes the current through it to be a constant, right. Now, what is going to happen is that initial current through the inductor is 0. So, the inductor is going to say I would like the current through me to remain 0, I do not want the current to change. So, when the current goes through a step response, current through the MOS device goes through a step response, what is going to happen is all of this current is initially going to come out of the capacitor. What was it earlier? When the inductor was not there, what was it? The voltage here was VDD. So, some of it as the voltage would start dropping, current would come through the resistor, right, more and more current would come through the resistor. Now, the inductor is blocking current through the resistor completely. So, all the current has to come from the capacitor, which means that the capacitor is going to discharge faster. All right. This is the step. Now, let us look at the next step. In the next step, what we are going to say, let us get rid of this. So, the current goes through a step. Now, imagine that the MOSFET, even though the current is really going through a step, there are parasitic capacitances here. Okay, significant parasitic capacitances are present. Now, when that happens, when the current is going through a step, the current through the inductors would like to be 0. The inductors like current through them to be conserved. Magnetic field should be constant, right? Energy is stored in the form of magnetic energy. So, the inductors are not going to allow any current to flow through them, which means that the capacitor, which was pre-charged to power supply, this parasitic capacitor is going to discharge. So, first the parasitic capacitor discharges, right. Now, the parasitic capacitors have discharged. Now, the inductors do not have a choice, all the current now has to come through the inductor, okay. And now, the same story starts again. Now, this inductor is going to carry all the current and the inductor on the top still says that no, I do not want any current to come from me, which means that all the charge on the load capacitor is discharged. Right. In the third step, what we are going to do is we are going to add another inductor over there, and what this inductor is going to do is it is going to say, hang on a little bit, this inductor is also going to block out current from this capacitor initially. Okay. And then when the current starts flowing through the second inductor, which one is it going to choose? Is it going to choose to come through the inductor capacitor series or inductor resistor series? It is going to choose to come through the inductor capacitor series, because at the right frequency the inductor and the capacitor together look like a short circuit. Okay. So, that is what you have achieved over here. Right. So, this particular circuit gives really good performance. Combination of these three inductors could also be modeled as a transformer. Okay. Now, this is where you have to ask questions. Why is this a transformer? How does this remind you of a transformer? Does it remind you of a transformer? Mutual inductance. Might have forgotten mutual inductance, right. The drop across the inductor is I1 times j omega L1, drop of the, so yeah. And what about here? Okay. So, these two look similar, these two sets of equations look similar, which means that I can model one as the other. Okay. So, as long as your mutual inductance is less than L 1 plus L 3 is less than the self inductances of each, you can model. That is usually the case. The mutual inductance is going to be less than the self inductance, because the coupling is ideally at best equal to 1. Okay. The coupling is usually going to be less than 1. Okay. So, that basically means that when I have these three inductors together, I can make this instead of making three inductors separately, I can make it as a set of two mutually coupled inductors. So, this is called the T coil. Something like this. This is called the T coil. The T coil is used routinely. So, you can insert a T coil into your so there is nothing else, right. There is your old circuit, your first cut circuit, which had your MOSFET, resistor, capacitor, load, and what you do is you insert this T coil. This is called the T coil. Okay. And suddenly your bandwidth is supposed to improve dramatically if you make the right T coil over there. All right. So, these are different techniques of making wide band amplifiers. Okay. These have been used time and again. I am going to discuss one more, which is using the principle of feedback. So far what have we seen? We have seen that we can, instead of having a regular RC circuit, we can introduce some poles and zeros, a pair of complex conjugate poles and a zero, right, and we can try improving the bandwidth. Over here, as you progress towards the T coil, you include more and more poles and zeros. I mean, these are more complicated systems, the order is much more. All right. So, you basically go to higher order. As you go to higher order, what happens? Suppose you make a linear group delay. Okay, what is going to happen? Is the group delay going to be more or less than the original? The group delay is going to become more than the original, right. So, what you have really played with over here, as you go to higher and higher order, what you have played with is the total group delay. You have made the total group delay larger, okay, and by sacrificing some delay, you have got more bandwidth. So, bandwidth, the circuit is faster, but the delay is more. What that really means is that things are coming faster, things are going out at the same speed at which things are coming, but the delay, the latency of the circuit is a little bit more. Typically, this is acceptable. Most cases, this is quite acceptable. The delays that we are talking about anyway are very, very small. Okay. So, the net speed of the circuit increases, but the delay you trade off. So, by trading off delay, by increasing the order of the circuit, by trading off delay, you achieve more and more bandwidth. All right. So, the other trade off is the gain. You have heard of gain bandwidth product, right? If I somehow decrease the gain, I can increase the bandwidth, right. So, that can be done by using principles of feedback. So, this is a very common circuit. And what I propose over here is, let us put feedback. All right. This might not be sufficient, you might need something like this as well. So, this is called shunt series feedback. So, you have put R in series and R in shunt to your amplifier. So, the shunt series amplifier also can improve speed dramatically by playing with the gain, right. So, what happens? You increase the bandwidth by a factor which is the loop gain of the system, right, loop gain of the system. Okay. So, shunt series feedback is also routinely used in a lot of different scenarios. These are used as wideband amplifiers. In fact, these are used at the input of oscilloscopes routinely. Oscilloscopes have to be wideband instruments. When you buy an oscilloscope, let us say it is a 1 gigahertz oscilloscope, it should be able to process all frequencies starting from 0 all the way to 1 gigahertz. So, that is what a wideband amplifier does. Okay. 1 gigahertz oscilloscope does not process only signals at 1 gigahertz, it has to process all frequencies between 0 and 1 gigahertz, right. So, it is a wideband system, and these are this particular shunt series amplifier, for example, is used a lot of times at the input as the input front end for an oscilloscope. All right. So, we are going to summarize over here what we have seen over the last couple of classes are basic techniques of improving the bandwidth of making wideband amplifiers. So, wideband amplifiers, what we did was, we said that yes, we know bandwidth estimation techniques and we know how to make better and better amplifiers using more and more devices, but these techniques have evolved over time when discrete devices were used, and as a result each and every device was expensive. So, each and every device was used with caution, and as a result you ended up with single device amplifiers with good bandwidth. So, we explored this particular arena and we saw that by the process of increasing the order of the load, okay, instead of a first order load, if I have a much higher order load, I pay in terms of delay, but I can get better performance in terms of bandwidth. So, that is what we saw. First we put one inductor over there, then we put two inductors, and then we put three inductors. Okay. And as I put more and more inductors, the system became more and more complex. I did not attempt to analyze these systems, I just hand waved my way through. I said qualitatively what happens. You really have to sit with a circuit simulator, or you have to sit with pen and paper real hard with probably some kind of software like Mathematica or MathCAD or something which can solve algebraic equations. and you have to work your way through the mathematics, and you will indeed see that you get significant bandwidth performance improvement. We also replace the 3 inductors with a pair of mutually coupled inductors. That is not difficult to build on an integrated circuit. 3 inductors is costly, more area. Mutually coupled pair of inductors is much less costly. You can build using the same area, one inductor on top of the other, or just double the area of one inductor on the side of other. That reduces the coupling though. So, one inductor on top of the other is preferred when you want a mutually coupled pair of inductors. So, that is significantly low in terms of area penalty, and you get the same net result. So, that is called a T coil. And then we did not really discuss the shunt series amplifier. This I am going to discuss in the next class, but kind of introduce to you that maybe you can pay in terms of the gain and improve your bandwidth. It is done a lot of times. Okay, thanks, and we will take it up from here in the next class. Thank you.